that brings us to the next question. What is required to actually make an object rotate? Here's my meter stick. It's not rotating. If I want to make it rotate, what do I have to do? So I either have to move my finger so I'm not supporting the center of mass. That allows gravity to pull the center of mass down. Or I could apply a force. And applying a force. Hey, you said apply a force. So I need to apply my force in a certain direction. I need to apply my force perpendicular to the object. Well, I can apply my force perpendicular to my object right here. I'm pushing down.
In relation to the center of mass.
So you have to apply a force, but that force must be not at the rotation axis. So it must be somewhere away from the rotation axis, and it must be perpendicular to the object. Okay, that's very specific. That's called a torque. For those of you who have had statics or will take statics, they call it a moment. Okay. Torque is simply a twist. In order to have a torque, number one, you have to have a force. You cannot have a torque without having a force. It's impossible. But not all forces will produce torques. So your force, number one, cannot be applied at the rotation axis. That would be like trying to open the door by pushing on the hinges. You don't get very far. Okay? If you apply your force at the rotation axis, it will not make the object rotate. So you have to have some distance from the rotation axis. Doesn't matter how far. You'll still make, as long as it's not right at the rotation axis, you'll still make it rotate. So even if it was a little bit away, I can still make it rotate. The farther away I get, the easier it is to make it rotate for any one given force. Okay? So you have to have that distance. We call that distance a lever arm. The distance from the rotation axis is called the lever arm. And then you need a force that's perpendicular to the object. If it's not perfectly perpendicular, then you only need the component that is. So here's our meter stick. Our rotation axis is right there in the center. There's my force. The lever arm is defined as the vector that points from the rotation axis out to where the force is applied. So we would call that an R. It's the radius at which the force is applied. Torque. The symbol we use for torque is the Greek letter capital tau. Torque is your lever arm times the perpendicular component of the force. So the force must be perpendicular to the lever arm. If you have a force that is not perpendicular, but has a perpendicular component, then all you need is the perpendicular component. We would break this force into a component perpendicular to the meter stick and parallel to the meter stick. You would only need that perpendicular component. Okay? Yes?
Isn't the x component affecting where it is though? Are you saying that
The x component doesn't affect where it is, no. It's still applied out here, but it only has a component that's actually perpendicular. I could have drawn this way. It's still out here. This is the perpendicular component.
So the force perpendicular, is that just F perpendicular?
It's the perpendicular component of your force. Yes.
Yeah.
Yeah, that just means that you want the component of the force that is perpendicular to your object.
The radius of,
To the radius, yeah.
yeah, radius of the force perpendicular.
Yes. You can certainly take the perpendicular component of the radius too. So it works both ways. Once you have your two vectors on the picture, find the component of one perpendicular to the other one. By the way, technically, the equation for torque is a cross product equation. I'll teach you how to do the cross product. The order of the cross product is important. R cross F is in a different direction than F cross R. Okay? So the order is important. I'll teach you how to do that. The only time you have to do the cross product, though, is if you have complicated vectors where it wouldn't be easy to find the perpendicular components. Kind of like the work when we did the dot product. It was easier to do the dot product if you had complicated vectors where you didn't know the angle, because the dot product took parallel components and multiplied them together. The cross product takes perpendicular components and multiplies them together. You get a vector answer. Torque is a vector. It means rotating clockwise is different than rotating counterclockwise. Now vectors. Vectors with rotational motion are a little screwy. We know, for example, if we had a force that way, the acceleration was that way, our object would either speed up in that direction or slow down in that direction. Easy enough. Rotational motion. Turns out the direction of the vector for rotational motion describes where the rotation axis is. So if I have my meter stick rotating clockwise, to find the direction, to define the direction of this, you use the right hand. It's called the right hand rule. You let the fingers of your right hand follow the direction that your object's rotating. So if this is rotating clockwise, I take the fingers of my right hand and let them go clockwise. My thumb is the vector. Okay? The direction of this angular velocity right here is in the negative z direction. Now it's a little screwy because that doesn't mean this object's going to go flying in the negative z direction. It's not going to move in the negative z direction. The negative z direction represents the rotation axis. My thumb is the axis. My fingers show me the direction around the axis that the object is rotating. Okay? So this way means my object's rotating clockwise. If it was rotating counterclockwise, let my fingers go counterclockwise, my thumb would be positive z. So the positive z direction means your object is rotating in the xy plane counterclockwise. That's what it means. So the direction of the vector is simply the direction that the axis is pointing in. So your thumb is the rotation axis. Your fingers show you what direction around the axis that you're rotating. So let's take our meter stick here. And hold it at the end. So our rotation axis is at the end of the meter stick. When I hold it only at the end of the meter stick rotates downwards. It's at rest initially, and it's speeding up on the way down, and then it slows down on the way up. If there's any change in rotation of an object, that means there's a net torque acting on the object. Similar to when we said if there was a net force on the object would accelerate. If there's a net torque on our object, it will have an angular acceleration. So it will spin faster and faster or slower and slower.
Usually there are free body diagrams like with normal force and force of gravity to try and find it.
We will be drawing our free-body diagrams, yes. Okay. So, for example here, what forces are acting on this meter stick once I've let go from this hand? Gravity. There's a little bit of friction between my fingers and the holder. There are centripetal forces in terms of just, that would be the bond strength between the atoms within the meter stick itself. Okay. So, number one, my fingers are keeping that end from falling towards the ground. So there's some net force from my fingers pushing up, pulling up, holding it up, whatever, however you want to word that. There's a little bit of friction between my fingers and the end there. That one's a little harder to draw in. Force of friction. It depends upon which piece of my finger you're looking at, because it's opposite the direction that it's rotating under my fingers. Force of gravity. Now the force of gravity acts on every piece of the meter stick, but we can treat it as if it were only acting at one spot. What spot? Center of mass. We can treat it as if the force of gravity acted only at the center of mass. If we want to treat the force of gravity as if it were acting at one spot, it has to be the center of mass. We can't do it at any other spot on the meter stick. Now, torque. The net torque acting on this meter stick. The torque due to my fingers. Well, my fingers are at the rotation axis. That means R is 0. If R is 0, then it doesn't matter how much force is there. It's not going to produce a torque. So R, for any force at the rotation axis, that force will not produce a torque. So the torque due to my fingers is 0. That upward pull of my fingers, that's not producing a torque. Okay? Not about that endpoint anyway. Now there will be a little bit of torque due to friction. The friction is going to be awfully small, as long as I'm holding really lightly on it. Are you okay if we go ahead and just say the torque is 0 for friction for now? Okay. It's a little hard to figure that out with fingers.
Question?
Yes?
Which way is your force of friction when you can't really read it?
That's the problem. It depends upon which piece of my finger you're looking at. There's no one set direction for friction. It's opposite the direction it's moving in. So each little piece of my finger...
Oh, so it's kind of on an arc.
Mhm.
It's an opposite.
Yeah. That's why it's really not easy to draw in, or to figure out in this case.